G'day, my name's Mark. Let's talk about quasi-linear first-order differential equations. So, what do I mean by this? It's quite a mouthful. When I say a first-order differential equation, I'm talking about an equation which contains derivatives of some function u, and all of these derivatives, because it's first order, must only be the first derivative of this function. What do I mean by quasi-linear? In order for a differential equation to be quasi-linear, what you require is that all the highest order derivatives, and in this case that's first order derivatives, must be linear. And in the case of a quasi-linear differential equation, we require these coefficients to be functions which can be any function really of the coordinates x, y, or even the dependent variable u. So let's look at some general forms of these first order quasi-linear differential equations. If the dependent variable, which is u, is only a function of one variable x, then you actually have an ordinary differential equation of the form a times du dx equals some other coefficient c. And these coefficients a and c can be functions of x or u. If we have more than one variable, for example, if u is a function of x and y, we would have some a times du dx plus some b times du dy equals some c, where a, b, and c can be functions of any of the dependent variables x or y and u itself. So let's just start by looking at a first order quasi-linear ordinary differential equation, that is, where u is only a function of one variable x. Our general form for our differential equation is something like this. So I'm going to work with this specific example. It's not immediately obvious how to solve this. It is exact, however, so it would be a good exercise for you to do to practice your ordinary differential equation skills. So you're not going to be able to get a solution too easily unless you have some sort of condition. So we'll give it some condition just so that we can find a solution. And if your calculations were correct, your solution should come out to be cos of sine of x times u equals sine of x times cos of u. So let's plot this solution. Let's just see what it looks like. It should look something like this. Remember, because we only have one of the points from the top branch of this curve, our solution that we can obtain is really only the top branch. What I want to draw your attention to is the fact that I gave you two bits of information. I gave you a differential equation and I gave you one starting point. So there's information in the differential equation itself which tells you what the solution should look like if you have that initial starting point. So how exactly do we get this solution from the differential equation? If we look at the original differential equation, we can rearrange it to look like du dx is equal to c divided by a. So we can see that any point on our solution should be tangent to a vector a, c, where a and c are functions of x and u, which are the points in our x and u space. So we can think of the x and u space which our solution sits in as having a vector field, and the solution is always tangent to this vector field. So we get a solution which is actually just the streamline of the vector field. We call these streamlines of the vector field that's derived from the differential equation a characteristic of the differential equation. So knowing that the characteristic or the solution to the problem is always tangential to the vector field AC, we can write down the solution in parametric form where x and u are functions of some parameter tau, and dx d tau is equal to a and du d tau is equal to c.